Well, thanks, Bill. Yeah, that was quite hyperbolic, I must say. But anyway, it's a pleasure to be here. Actually, since Bill mentioned it, the first paper on laser cooling, we wanted to call it laser cooling. And the editors rejected that idea. So we had to say radiation pressure cooling, bound absorbers or something like that. Anyway, as you can tell from the title, this is going to be kind of down in the trenches. I don't have any main theme here. So just to summarize a little bit, not everybody is maybe familiar with what Chris does here, but for Chris's guys, the first part is you'll know it well. And we've been over the last couple of years or more now, we've been kind of focusing on trying to improve our logic gates, particularly the 2-qubit gates, and those are the hardest ones to get accuracy or fidelity on. And so I'll talk a little bit about that. I'll say a little bit about our efforts towards scaling, and we as and we're behind what Chris Monroe and people like Rainer Blatt can do in terms of simulation, but I'll give you kind of an idea what we're trying to do there. And then there's, one of the main problems that we all have is this problem of heating. I'll say a little bit about that, and just for fun, I'll talk about this is a little bit kind of a separate topic, but I'll get there. And if I have time, these are projects in process, so I'll try to say a little bit about that if there's time. So I think you probably heard this from Chris if you're not familiar with, but we use this linear quadrupole trap, which is kind of like a quadrupole mass filter, but it's plugged on the ends if we put, say, positive potentials on these end segments versus the center ones. Anyway, I'm not going to describe the traps. You can think of a 3-dimensional harmonic well. We typically make the binding along this horizontal direction relatively weak to the other ones. And so the ions, if we put ions in the trap and cool them down, they'll want to form a linear array like this. So the simplest case to think about for quantum bits is, say, 2 optical levels. And this is what Rainer Blatt and his guys do, for example. They use typically, for example, the S and D levels in calcium. They've done a lot of work on that. So I think Chris and I have focused for a long time on rather than using optical transitions, is to use hyperfine levels. And one of the main reasons for that, of course, is that the radiative lifetime is extremely long. The other thing is you don't need very precise lasers. What we do is we drive stimulated Raman transitions. And so if these two, pardon me, let's see if I can get this back. If these two beams are derived from the same laser, say offset with a AO modulator, then you don't need to control the overall frequency of the laser very well. And what matters is the difference frequency, which can be controlled in RF. And so for example, to drive spin flip transitions, and here are the typical numbers in beryllium and magnesium, two of our favorite ions to play with. Then to drive spin rotations or spin flips, we use co-propagating beams and anyway, go through virtually through these excited levels. And one of the things I'll describe later, one of our limitations is you always have there's some amplitude in these excited states, and we have to worry about spontaneous emission. But if we can increase the power enough and detune far enough from these excited states, then basically the spontaneous emission goes as 1 over the detuning squared, whereas the Rabi rates on these Raman transitions goes as 1 over the detuning. So if we can increase the power enough and detune far enough, we can suppress that. But it's still a problem for us. And then we want to be able to couple to the ion's motions, and so we need to do that, we need to have some difference in the k vectors of the beams. And for most of our experiments, we typically are accessing the modes of motion along the axis. I know Chris has more shifted now to coupling to the transverse modes. But in any case, for the axial modes, we want to have, ideally, we want to have the difference of the k vectors to align along the z-axis in order to couple the internal states to the motion. And this gives this diagram here gives an example of where we're, in this case, we're driving what we might call the red sideband, where we start from some motional level here, and we can decrease the motion by one unit of one quantum of motion. And then the typical thing, of course, in a lot of atomic physics experiments, we can get pretty good discrimination by scattering off of a transition where, in the simple picture here, we tune the laser to this transition here, and this one is off resonance, so we can see photons when we scatter on this one and very few photons on this other transition. Of course, in order to make this work, we want to use circular polarization, and we want to go from the highest angular momentum state, say in the lower state, to the highest angular momentum state in the upper state. And this, because of selection rules, then if we excite this transition, it has to decay back into the ground state, and we can cycle this and even though we only need to sample a small number of the scattered photons, we can get good state detection this way. Okay, so that's the basics. And then the other thing, which it's very similar again to what Chris is doing, is that there's different ways to describe these gates, but the one we've thought about is basically this idea of displacing a motional mode in phase space. So now this is focusing on the motional modes, and here's x and p. So this is the phase space of a particular mode. And as described by these guys down here earlier, basically, if we think about displacing the ion or the wave packet of the ion in phase space, it turns out that we pick up phase shifts, and if we can integrate over small increments over a closed path, and it turns out we accumulate a phase shift and by closing this loop. And so and basically we want to make this, to get a gate, then we want to make the force state dependent. And so, for example, we'll adjust things, and I'll say in a minute a little bit more, but we adjust things. So, for example, this is a universal gate where we kind of realize a truth table like this. And to get the state-dependent forces, like everybody else, we use optical dipole forces. So an example of how this works, so again, we're going to focus on in our case, for these modes along the axis. And so for two ions in the trap, there's two modes of motion. One is where the common or the center of mass when they're equal mass motion, and the so-called stretch mode. And so the way that you can think about this working then is we set up these we set up a standing wave, but in this case it's a moving standing wave where the frequencies of these two beams are detuned from each other. In this case, we're gonna excite the center of mass mode, but slightly detuned from this. And so the picture we have then, in this case, let's suppose we have, doesn't need to be this situation here. I'm just assuming the forces in the up state are common, and there's no force in the down state. Basically, we just need a difference, though, in the up and down states. So in this cartoon here, we show this moving standing wave sweeping across the ion. In this case, for this case where the force on the upper state is the same, we want to space the ions so that they both feel the same force. And in fact, it's more typically on the order of 10 of these standing waves that they're separated by. But nevertheless, we can get this common force. Part of the reason for doing that is that the stretch mode then well, we're off resonance with the stretch mode, so we don't have to worry about exciting that. But in any case, so what we end up in this phase picture, we're detuned slightly from the resonance, and so what happens is that this force on the ions that in phase spaces causes the ions to go around a circle. And then for this particular, pardon me, I'll get it here. For this particular example, if we start out with a state that's shown down here, for example, then there's no force on the component of the state that has both spins down. There's a force that on the states where one spin is up, then which gives an area proportional to the force, and sorry, pardon me, the force is the area is proportional to the force squared. So what happens then when we're for the component of the spin where there's two spins up is that the area covered by in this loop in phase space is 4 times what it is for when just one spin is up. So we get something like this, and basically what we do then is we adjust the phase this to be this example pi over 2, and that's exactly then gives the phase gate that I was describing here. Okay. Okay. And so a couple caveats here. For high fidelity, we'd like to be in the regime where the force is linear, and so in order to satisfy that condition, basically we want the statement is you want the amplitude of the motion to be much less than the wavelength, the effective wavelength of this moving standing wave, and so that's basically the so-called lambda decay regime. It also turns out that this particular a disadvantage of this particular gate is it won't work on field-independent qubits, and I'll say what I mean by that. But basically, one of the problems we have to worry about that govern the frequency separation of the qubit states is magnetic fields, and so we'd like to find transitions where to first order the energy separation of the qubits is independent of magnetic field, but that also corresponds to the condition where we don't get differential forces between the spin down and the spin up states. So we can't use this particular gate on these field independent qubits. Okay, so nevertheless, one of the groups, Molmer and Sorensen, who proposed these gates originally, they also proposed a phase gate, but in this case, it's in the basis, that so-called XY basis. So in these, for example, here's the state that we're going to act on with these forces, and in this case, it's very much the same idea as I described for the phase gates on the previous few graphs, but in this case, the forces act in the XY plane. And actually, a lot of this is summarized in a paper by Chris Monroe's group from about 10 years ago. Nevertheless, so what we do to realize the forces, it's a little bit more complicated. In this case, we need to illuminate the ions with beams that excite both the red and the blue sideband at the same time. So we need a minimum of 3 beams for that. And one of the nice things that we picked up on this paper from Chris's group is they there's different ways to drive both red and blue sidebands at the same time. But the nice thing that Chris and company suggested in this paper was it's sort of a practical advantage, and that is that we can excite these red and blue sideband at the same time by having this beam over here, and then two other beams that are separated by nominally the hyperfine frequency, and then plus or minus the motion frequency. And a key technical advantage of this was that basically you can, with a single, say, AO modulator, you can generate both of these beams at the same time. And the reason that's nice is that you can get them to follow essentially the same optical path, so that the differential phase shifts due to air currents and things like that, they're common to both of these beams here. Now we have to worry about over longer times the differential phases between this pair of beams and this beam here. But what also in this same paper of Chris's group, but they suggested a way around that. Okay, that's just what I said, that over a long time, the phase between these paths here and this path here can wander due to like air currents and vibrations of mirrors and things like that. So what in this same paper then, what they suggest is to sandwich this state-dependent force which acts on these states up here, but between two pi pulses that basically, so again, we'll start out on the plus minus basis, or excuse me, the spin up, spin down basis, and then if we apply a pi over 2 pulse, which then creates these kind of states here, then basically at least over the time it takes us to do a gate, basically we can, with these pi over 2 pulses, if we control the phase of those gates, basically taking one of these beams and this beam here, then basically we can orient the spins in the XY plane such that they will always be aligned with the force given by this Molmer-Sorensen scheme. And then basically we undo it with a second pi over 2 pulse here. And so basically what that does is it makes again a gate like I talked about in the previous screw graph, a ZZ gate in the spin up, spin down basis. And in practice, as I say, is if we do this combination of the Molmer-Sorensen gate that acts on these states sandwiched by these 2 pi over 2 pulses, if that can be done in a time scale fast compared to the beam fluctuations due to air currents and things like that, then basically we've accomplished this ZZ gate, and we don't have to worry about the fluctuations over long term. So this is a strategy we've been using based on their suggestion. In the first problems, in the first experiments we tried, we still had problems, particularly with we still had problems with these difference in path lengths, and the fidelities weren't anything to shout home about on our first tries at this gate. And so actually in this paper here, we were just trying to more focus on this benchmarking technique, but the fidelities weren't actually very good. And so one of the things, and it was mainly because still these problems of the free space beams. And just to give you an idea, typically one of the problems we have, we always looked with envy on Rainer Blatt and company, who were working on transitions in the visible where you could get fibers. And the nice thing about that is you can bring the fibers up close to the trap and make the path lengths between the launch point of the beams and the ions fairly small. And we had suspected this was the biggest problem we had, because literally with all our AO modulators and so on between the generation of the UV beams and switches and frequency shifters. The beam paths were a few meters long, and there are lots of air currents and things to vibrate to shift it. So that's the problem we had. So as I say, we always looked with envy on having these fibers. So for a long time, we had been trying over many years to try to find a fiber that would work. And typically what happens with most fibers as you buy them, if you stick UV in them, they'll form color centers. And these color centers literally can form over the time scale of hours. And so it was a killer. And, but anyway, one of our postdocs, Yves Coulomb, did some researching and found this idea had been realized before on multimode fibers. And basically, it sounds like magic to me, but basically the idea, anyway, let me just describe what the recipe, what we do is we take fibers, and they can be commercial fibers. In our case, they're solid core silicate fibers, and this picture here shows the beam coming out of it, but it's a solid core. It's got this photonic crystal band gap structure to confine the mode, but they are solid core fibers. And basically what we do is we put these fibers in a hydrogen cell. It's about 100 atmosphere, and we leave it there for about a week. And then we expose it to the UV, the same UV that we want to transmit. And it turns out apparently it still makes color centers, but the color centers absorb at wavelengths that are different than the one we're transmitting. And this was a really big thing for us. And in fact, in some of these experiments where we're typically transmitting up to 100, on the order of 100 milliwatts, we've had the fibers now last a year versus an hour before. So it's been a big help to us. And actually, if anybody's interested, one of Stan Slichter put a recipe there, and I can give it to you later if you don't catch it now. Anyway, so coming back to this same picture, basically now we're at these levels of fidelity, and we didn't do a direct comparison, try to substitute fibers and then a free space pass, but it almost certainly is because of our ability now. We can have these fibers that are up very near the trap. They do two things. One is they minimize the length of free space that you have to go to from the launch point to the ion, and also the mode gets improved a lot. So in this other view graph, you saw this picture here. Here was for this test experiment. Here was this mode input, and it, of course, cleans up the mode. And actually, in our beam paths, these long beam paths with all the modulators and so on, the modes looked a lot worse than what I show here. So anyway, those two things I think really made the difference. And I should also say that actually the Oxford group, I think they might have posted this week. They've actually had these similar fidelities longer than we have, over several months. And anyway, they posted a paper on there. So we're both at about the same level on these fidelities we get now. And so the one limit we have, again, is spontaneous emission. And I mentioned briefly before, the spontaneous emission goes as 1 over the detuning squared, the overall detuning from the optical excited states. And you can compensate for that by increasing the power and then detuning farther. And we actually, these results here, we're almost up to a watt now. But the one thing we can look forward to in reducing the spontaneous emission error is this pink overlay gives you an idea roughly the size of the beam. Actually, they're about twice as big as this picture shows. And so clearly we can win by focusing. It means we'll have to control the position better, but I think we can win a lot and suppress this spontaneous emission. So we're hopeful that we can even do better in the future on this in terms of the fidelity. Okay, so one thing we've also been thinking about, and I know Chris and company are thinking about that in their idea of being able to do quantum networking, and is to use a hybrid system. That is where you can maybe use the particular advantages of two different species of ions. And we also have some ideas, not for this quantum networking, but there's some other things to think about where this might be useful. I mean, actually, we've been using, in some ways, we've been using two species for quite a while, and that is, in our experiments, we've done a number of experiments where we mix both beryllium and magnesium, and the beryllium are our qubits in these experiments, and we can, if we also put trap at the same time magnesium ions, we can laser cool the magnesium, and that will keep the ions cold, which we need for these to preserve the fidelity on these gates. And the nice thing about that is that we don't have to worry about scattered light from the cooling, because the wavelengths are quite a bit different. And also, I mean, it allows us to go longer and longer times and keep the ions cold. That is, we use the magnesium to keep the beryllium cold, and then we can preserve the fidelity of these gates. So we've been doing that, this so-called sympathetic cooling, for quite a while. I mean, there's some other things that would be interesting. For example, in all of our experiments, we have these big wide beams, and so we can't easily avoid scattering, say, in our case, since we have such weak focusing, if we try to just scatter light off one ion, we can't, because the excitation light covers all the ions. And so the idea is maybe by transferring the qubit state information between the species, then we can detect one ion without interfering with the coherence of other adjacent ions. And also, one of the things we were hoping to take advantage was with these dual species gates, which I'll describe very briefly in a minute, is that we can improve state detection efficiency, because I didn't really explain, but these gates, like the Mulmer-Sorensen gate, all you need to do is, you don't have to be in specific motion quantum states. You just need to be in the Lamb decay limit, where the extent of the motion is much less than the effective wavelength of light. And Chris and company, they've been thinking about these quantum networks, and so the basic idea there is that maybe you could have one ion that's good for memory. I think they have plans now to use ytterbium as their memory qubit, and then transfer the information to an ion like barium, which they can couple then optically, different locations. And so the idea that, so this transferring information might be useful in that scheme as well. In any case, what we...
Dave, before you go on, could you say something about dissipative entanglement?
You know, I wasn't going to... I wasn't going to include that, but I'll give you something. This so-called Zeno thing is close to that. But I wasn't going to discuss our dissipative entanglement experiment. But anyway, so our system then, we'll play with our favorite ions, which are beryllium and magnesium. As I mentioned before, we typically go to a field where this particular hyperfine transition in beryllium at about 120 Gauss is field independent. And that means to first order, the frequency doesn't change with magnetic field fluctuations. And on the other hand, of course, it would be a miracle to have that field independent qubits for both magnesium and beryllium. But nevertheless, there's a transition in magnesium where the field sensitivity is not too, here it is. It's not too bad. It's almost 50 times lower than it would be if we were close to zero field. So it's not field independent, but at least the field sensitivity is reduced with magnesium. So this is the qubit level in magnesium we're going to use, and this is the qubit levels in beryllium that we're going to use. So in this case, it's the same story again, that all we're going to do is double up the number of beams. So the red is to represent the beryllium beams, and the green is the magnesium beams. And the only thing, of course, we have to, again, we want to synchronize the forces in the XY plane of this Molmer-Sorensen gate. But it turns out in this arrangement, all we need to do is synchronize with RF, the frequencies we're creating the red and blue sideband. So it's there's a tune-up process there, but we can again, we get all the advantages that I described before that were laid out by Chris and company before, and we're just doubling up now, and we just need to synchronize one RF phase to get the forces the same direction in the XY plane in these schemes. So anyway, and again, one thing to say is that I said it briefly before, but our typical beams are fairly broad, and so, but nevertheless, because the wavelengths we need for beryllium and magnesium is so much different that any operations we do on beryllium, even though the beams are overlapping with the magnesium ion, they're so far detuned that basically we don't get any interference or any decoherence or phase shifting from those beams. Anyway, so if we first just invoke this Molmer-Sorensen displacement, it turns out we don't need the pi over 2 pulses, and we can generate a state that looks like this. I forgot the normalization here, and in fact we can get reasonable fidelities with this. I forget whether I marked it down here. No, I didn't. In any case, but in order for long term, that is over many operations, again, this is what I described before. We take this Molmer-Sorensen gate and we sandwich it between these pi over 2 pulses that we first invoke and then undo on this second step. And from that, we realize this phase gate, which I described originally over here. So the fidelities aren't real high yet. Actually, they're on the order of 98%. And the reason for that is it turns out we don't have as much power with a magnesium beam, so the biggest problem we have is spontaneous emission on the magnesium transitions, but nevertheless we can still get reasonable fidelities here. Actually, just for fun, the Bell inequality measurements seem to never go away, and so it's always interesting to think about different contexts. So here we're playing the game where we're entangling 2 different species altogether. We make a Bell state, and we can perform a CHSH type Bell inequality. And anyway, so just as an aside, we did this experiment where we looked at the Bell inequality, and it's violated by some reasonable number of standard deviations there.
Does that also close the detection loophole?
Yeah, so yeah, Bill is asking. So just recently, in fact, there's a group from Delft who reported the so-called the first loophole loophole-free test of Bell's inequalities, and so nobody believes that, there's a problem, but for many years, ever since this game started, people wanted to do a test where you could, first of all, ensure non-locality. That is, so you have, in the photon experiments, you create an entangled pair, you separate them, and you want to be able to do detections on a time scale and selection of your detector orientations on a time scale where there's no way that what you do over on this side could communicate with the other, and that's sort of the locality loophole. And the other one was that in the photon experiments, they typically, detection efficiencies were not so great, that they had to assume fair sampling, meaning whatever data they recorded, it was a representative of the sampling. And I mean, nobody believed that it wasn't that wasn't true, that you weren't getting a fair sample. But the purists say, well, you have to have detection efficiency high enough so then you record every event so you get around this problem that maybe you're only detecting those events that say Bell's inequality is violated, whereas if you could detect everything, then they would be preserved. But anyway, even though nobody believed that, you wanted to do both things at once. And recently, there's an experiment at Delft that was able to do this. It was actually similar to the ones that we did. We were the ones, I think, that did the first Bell test that got around this detection efficiency loophole. But recently now, the photon experiments, the detection efficiencies are high enough that they can do both. And there was an experiment by the Delft group and there's an experiment by Zeilinger, and there's actually one at NIST, Se-Woo Nam and his guys, and they're a little bit behind the curve, but they're scrambling now to get a publication because they also have done this loophole-free test. And anyway, that's a bit of a diversion there, but.
I might mention, if I'm correct, we're going to have a talk about that on Wednesday, right?
Yeah, Se-Woo Nam is going to.
Oh, okay, so you'll get you'll, sorry, I didn't mean to steal his thunder there.
No, advertising is always good.
So I mean, there was this, it seems pretty clear, at least from my distance, that, the Delft group, I mean, they had to take many hours of data to get some statistically significant, and I think in Se-Woo Nam's experiment, they got a lot more data, a lot better statistics, and of course there's always a rush to be first, but I think if they get within 2 or 3 months, that'll be a tie in the long run, so, because they've been working on these experiments for a long time. Okay, so we can apply this two species gate, and for example, we can make a controlled NOT gate. So here's this is the gate I just described in the blue box here, and so we can make this controlled NOT gate where we carry out this mapping here. And this is useful, for example, if we're trying to detect the probability of one state or the other. If we do this controlled NOT gate, we get this entangled state, and then if we detect the second species here, then we can basically we're detecting then but through this mapping process, we're detecting the populations of the first state. So that's one application. We've also concatenated 3 of these gates to make a swap gate. So, and in this case, basically the idea of a swap gate is that if you have two input states here and here, basically it just swaps the states. And so as a simple demonstration of that, we did an experiment. We did kind of a Ramsey experiment where we started the magnesium out in an eigenstate, and in the beryllium we made an equal superposition of the up and down states, and then through this swap gate, then we mapped the Ramsey state with some phase delays, and this is kind of a Ramsey experiment where the first pulse is on the beryllium ion, and then the second pulse is on the magnesium ion, and then we detect that. And these are sort of the fringes. You can see it's not great, but it's on the order of 95% contrast there. And this will also be useful, we think, for detection. That is, to be able to map our qubit states onto some other ion that we detect. And there's several applications in quantum error correction where this would be a useful procedure. Okay, so what about scaling? And this is sort of an artist's dream of how we might do this. And the basic idea is that the simple thing to say is that I think in the kind of gates we and Chris are using, you need to control these motional modes. And the simple statement, if you want to scale up to very large numbers, it's probably going to be hard to control all these modes. And so the simple idea is one idea of scaling is to have an array of traps where you have a relatively small number of ions in any given trapping zone. And then in order to scale so that you can manage these different modes. And one way to scale up I mean, Chris and I and Dave Kopinski wrote a paper a long time ago about one way to scale up is to have this arrays where you, in this case, where you move ions around between these different zones of the array, and to be able to control the numbers. And of course, another one that Chris is and his group is pioneering is, anyway, and this is just again thinking about this scaling in terms of long-term operations is that we want to be able to cool the ions down, so we have some ion we can sympathetically cool with. In our case, it's magnesium, and sort of the simplest version of this might be is you might consider a packet that you move. You keep a logic ion, in this case beryllium, and then an ion to keep the ions cool, and you move those around in this array. Another version of how to couple these different zones or zones that are separated by wide distances, what Chris and company have pioneered, and that is, I'm not going to describe this, but basically what they've shown is that you can entangle the internal states of qubits, say in their case ytterbium, with the states of a photon, polarization states of a photon, and you can do projective measurements if you do those entangling operations on two separated ions, and then you do a projective measurement, you can actually entangle these separated ytterbium ions. So that would be a way also of scaling up, that is connecting the qubits in these different zones of the array. So anyway, coming back to this idea where we move ions around, one of the things we've been trying to do is improve our ability to move ions around as quickly as we can without getting too much motional excitation. This was an earlier experiment by Brad Blakestead, one of the students who was actually a postdoc here, over at NIST, right, for a while. Anyway, in this case, the idea was to move ions around adiabatically, and the picture there is you have some well, and you're going to translate the well to different locations, and so in this apparatus that he built, we call it X-trap because it has this junction. He was able to demonstrate moving between these various zones, and if he did it slow enough, and in this case, it's on the order of several hundred microseconds. In other words, adiabatically move the ions. He would get excitations of less than a quanta during these various transfer processes. And you'd like to speed this up. And so one of the things we've been working at off and on is to do diabatic transport. And the simple idea here is that for a single ion, which you can think about as in the limit, if you can preserve the shape of this harmonic well, but if you can suddenly jerk it, say, over to this position on the right-hand side here, the ion, will as you move this thing over, the ion will be raised up in this harmonic well, and it'll fall down the well. And as long as the well is kept harmonic, if you start in the ground state, the ion it'll preserve the wave packet size. And in this case, the idea is that, the classical picture works here is that you move the ion over here, and it's going to oscillate back and forth in this displaced, as it moves along, it'll oscillate back and forth. But basically, you catch it at a time where it's going back, and you stop it when it reaches the bottom of the well, and in principle, you can catch it back in the ground state. So that's the kind of idea we've been playing with this, and one of our students, Ryan Boulder, did an experiment, and I'm starting to run, I think, long on time, so let me just say briefly that we do basically what I described. And so in his experiment, he would first cool the ion to near the ground state, and then he would move the well rapidly, and then in this second well, he would apply a red sideband, which means that if the ion, if the ion has any excitation at all, it will then be, you'll be able to flip the spin through this transition here, and then he would transport adiabatically back to the original position, and he could measure that excitation by driving these sidebands. And so this picture here is meant to demonstrate the fact that the excitation was pretty low. So if there was no excitation at all, this upper curve would be a flat line, and you'd see full oscillations on this. But nevertheless, you could show from this that the change in excitation would be on the order of a couple tenths of quanta during this transport. And in this case, rather than a few hundred microseconds, you could get it down to less than 10 microseconds. Anyway, there's a lot more to do on this. We've done this with 2 ions, or he did this with 2 ions, and we got similar results there. What we'd like to do, though, is we'd like to do it on this packet that has both magnesium and beryllium. And there the situation is a lot more complicated, because even with 2 ions in the simple picture, in the way I described, you'll excite the center mass mode of motion, but you won't excite the stretch motion. But with 2 dissimilar ions, then you tend to excite both modes. So it's a bit harder, but we're trying to improve on that as we go along here. So that's the challenge. We're starting, or we have been working on this, and we still need to do more work on that to try to do fast transport, but keep the motional excitation down fairly small. So anyway, the other part of scaling, which we've been working on for quite some time, and other people have been as well, and the basic ideas here, this is the kind of traditional 4-rod quadrupole structure we've been dealing with, and quite a while ago, you could distort this electrode shape. If we look along the end of this thing, and these are squares rather than circles, but it'll give you the idea. So it turns out we can distort the electrodes into a plane, and then still have an axis of trapping, which basically simulates what's going on in this picture here. And of course, the big selling point about this is you can then use, microfabrication techniques, using lithography and so on, to make these kind of traps. And this is kind of a stunt we did here, where we made this trap, so-called racetrack for the obvious reasons. But each one of these little squares is then a zone where we could capture a few ions and manipulate them separately from the other one. I mean, we didn't get very far with this particular trap, but we were trying to progress with this idea. I think John Bollinger was here, right? So I won't say much about this, but he described these experiments. This is a different kind of trap for those that didn't see it. It's ions in a penning trap, but the basic experiment he describes is where in this penning trap, where you can make pancake arrays, in this case a triangular lattice. And the thing he is pursuing is this idea of being able to scale up to larger numbers in these simulation experiments. It's very close to what Chris and company are doing, in this case in a 2D array. And I know they're getting together a paper. They've finally seen spin squeezing on this in these experiments now, and you'll hear about that pretty soon. I think they'll get a paper on the archive. Nevertheless, our neck of the woods with these RF traps is slightly different in that we want to try to make arrays. In this case, kind of a cartoon version is that we'd make based on these on a geometry of traps. Basically, the idea is to have individual traps where you control the shape of these 2D arrays by just the geometry of the traps. And so this is the kind of idea we're playing, looking towards the future, but we're not very far along. Nevertheless, as a first crude step in this direction, we've made in this demonstration, we've made two adjacent wells where we get the ions at least close enough together where we can start to see these effective spin-spin interactions through the dipole-dipole coupling of the ions. And I won't say much about that. We're just in these first baby steps of trying to make an array, but this is kind of the first step where we have two separate zones where the ions are in separate zones, but they're coupled through the Coulomb interaction. And I won't say much about that to say, but we would like to go smaller. The couplings in these experiments were only on the order of few kilohertz between the ions. And we would like to go smaller. Basically, the coupling goes as 1 over the distance between the ions to the third power. And so the exchange we can get much higher if we could shrink it down. The problem that we have and everybody has is if we try to make the trap smaller, we get this heating problem, which nobody understands yet, but it's fairly ubiquitous in all these ion trap experiments. And so anyway, we've been kind of trying to work around it for quite a while now. One thing we found also with Hartman Hefner in Berkeley is also seeing the effect that, the obvious thing to do, I think over the years we suspected that it's stuff on the surfaces was giving noise, and we don't really know what it is, but one obvious thing to do, which surface scientists do, is they clean their electrodes, and one way of doing that is with argon ion beams. So we tried that, and we actually could reduce this so-called anomalous heating, since we don't know what it is, by about a factor of 100. And yet we still don't really know. So we've been trying to collaborate with, there's a surface science group at NIST, and so we've been collaborating with them, and also some theoretical help from Hossein Sadiqpour at ITAMP. And the basic idea, kind of the crude version of what we're trying to do is we've made this trap, we call it a stylist, because the idea is it kind of holds an ion above this array of electrodes. And then the idea is to bring up samples of different surfaces that we can, in vacuum, we can either coat and do the different cleaning procedure, and just try to find out, maybe get a correlation on what the surfaces are like and what the heating rate is. So it's going to be a very slow process, but we started along this path here now. And I probably will run out of time before saying about the experiments on that, but let me move on here. And this is a bit tangential, but it's still kind of fun to think about nevertheless. So this is kind of a demonstration of what's become known as quantum Zeno dynamics. Now the Zeno effect, historically in physics has meant that if you measure a system, you suppress its dynamics. And the basic statement there is that almost in all cases, if you start a system out in an eigenstate and you apply a perturbation, almost any perturbation, at least for short enough times, the population evolution out of the initial state goes quadratically with time. So if you measure the system often enough, you can suppress this dynamics. Anyway, this stuff called quantum xenodynamics, there's really not a measurement, so I don't really so much like the term, but anyway, you don't have to, anyway, that's what it's called. But anyway, so kind of a simple problem. There's been other demonstrations of this kind of dynamics. But anyway, so one of our graduate students, Yiheng Lin, came up with this real simple demonstration of this idea. So think about two spins. If we start out, say, if we start out with the ions both in the spin-up state, and we think about, in fact, we apply microwave fields uniformly to both ions. And if you think about the two ions, actually, they continuously evolve between both spin-ups and then the triplet state, that is spin down, spin up, plus spin up, spin down, and evolve continuously to the down-down state. So you can think about, but the picture you can have in mind too is both these spins are just rotating in this common field, and there's never any entanglement. But the idea then is this, in this simple demonstration of this Zeno dynamics, is that if you could somehow inhibit this last step, then then maybe you can just leave this simple rotation operation on and go from this unentangled state, the up state, to this triplet state, which is then entangled. And so the basic idea in this experiment, the way you can do this, is basically you're going to stark shift this lower level out of resonance. And the way this works in this particular demonstration is basically we apply we start the ions in their ground state, the n equals 0 state, and then we apply an excitation near this, the so-called blue sideband, where we're changing the quantum number by 1, and we get this coupling between these three states. But nevertheless, we now have a dress state system between this original level and these other two states. And overall, then, what that means is that for the microwaves that are trying to connect this level to these levels downstairs, they're now shifted off resonance by this through this.
States also shifted by a different amount.
No, in this case, no. I mean, at least if we start in n equals 0, it's not shifted. And the reason for that is just that we space the ions well. For example, you might worry about there's this transition here. The way we do that is just we space the ions in such a way that this excitation is canceled. And so anyway, we basically these levels remain, at least in idealized, they remain untouched. And this, so the selling feature of this, at least in principle, is that one nice thing is that the complicated interaction, there's these sideband interactions. All you're trying to do is stark shift this level away from the resonance condition, and so you don't need to control the intensity of these lasers very well at all. You're just trying to shift them out of the way. So to first order anyway, you're really insensitive to the Rabi rates on these transitions, and also even the motion frequencies that allow, they're undergoing this sideband excitation. Anyway, so in this demonstration here, experiment, you can see we start the ions out. I'll just briefly go through. This is the red here represents the ions, both spins, 2 spins up, and you can see this evolution. And it actually works pretty well. You can see the green curve is the one you want to follow. This is the probability of the triplet state, and in this experiment, it's up around 98%. But the one thing about this, even though we're not so far detuned from these dress levels that there's some amplitudes in those states, so you can kind of apply a spin echo effect to put whatever population is in those dress state, at least to first order back in or cancel them out, those populations. And so this second data shows this where this spin echo is inserted. And so in this case, we get up above 99%. And this is just where we've only realized a situation where basically the detuning of these stark shifted level is only about 7 times the Rabi rate this is the Rabi rate of the microwave excitation. So it actually works pretty well, and although this still can't compete with the best fidelities that we're seeing today, it still might be actually a useful technique in some instances. So I think with that, I had a couple of other topics. Well, anyway, yeah, we're stuck with spontaneous emission on this one too, which we hope we can solve by focusing the beam down. This does have the disadvantages that the errors, you really want to be in the ground state for the simple scheme to work. That is the initial motional ground state, and so we do have this error that the errors go as roughly the fraction of population that's in the first excited motional state. So there is that drawback. Anyway, and we could extend this to 3 ions and make a W state there with certainly less fidelity. So I'm not going to. I think since I have run over. Let me just say I was going to say there's 2 other topics, and one is we're trying to do gates. They're based all on microwave transitions. And this idea of these microwave gates, particularly for the 2-qubit gates, and there again we want spin-dependent forces, and the way we get those in these microwave experiments is goes back to Stern-Gerlach. We're getting the forces from inhomogeneous magnetic fields, which in this case are RF fields, but the idea is we want to generate. We can make these forces state-dependent and invoke the gates. Formally the gates look exactly the same. The only difference, rather than using optical dipole fields to get these state-dependent forces, we're using inhomogeneous RF fields. So that's that topic, and I won't say more. So the other thing we've been doing is actually this comes back to Sewu Nam. So one of our postdocs, Daniel Schlichter, is collaborating with one of Sewu Nam's guy, Varun Verma, to try to use these very high detection efficiency transition edge detectors. So Sewu's going to describe these things. I won't describe to you these detectors, but what the interesting potential application is that the idea, well, I'll show you the cartoon anyway. We have kind of a test experiment. It's not quite working yet, but the idea is to put one of these detectors underneath an ion. And so basically you're just capturing directly the scattered light from the ion. And they can be very high efficiency. They can be over 90%. They're very fast. And we anticipate being able to do as well as we can on detection efficiency with our F1 optics, but it's not working yet. We've got the ion trapped separately, and we got the detector to work, but there's been some other problems. We haven't made this work, but we hope to take advantage of this. And the idea, the sales pitch for scaling anyway, is that there's no optics in this experiment. You could, in the long term, we think about for detection, you'd move an ion that you want to detect over a zone like this and then be able to detect it. And of course you can parallelize it. And it's just a few, 2 leads coming out of the apparatus to do this. Anyway, I won't describe that. Actually, we're trying to develop some software. I think we've talked to a few people here about trying to, a software that might be useful for for the ion experiments and maybe for some of the atomic physics experiments. I can say a little bit more about that for people offline if they'd like to hear. Anyway, of course, here's the people really doing the work. This, unfortunately, a little bit out of date now, but it gives you a rough idea of the size of the group. And with that, I'll stop. Thanks.